Thank you. Thank you very much. And also I'd like to thank Jerry Gao for initiating this invitation and Jane Wu for helping me out with the presentation. So my objective, you notice I talked about barriers and leapfrogging them. It will be to discuss certain red flags which are emerging within the semiconductor industry. They've been around for a few years. Now they are becoming visible and painful. Machine learning and AI, artificial intelligence, should enable us to leapfrog or decisively jump over those barriers. The need for AI now is not just a nice to have need, it's a must have imperative. There are 5 key messages I'd like to leave you with. Sorry for the long list, but first, the transistor scaling continues. The original Moore's law on the surface is alive and well. But right underneath the surface, we have run into problem with what I like to call Moore's law number 2. It concerns cost, which is now shooting up and not trending down as it did for many, many years. The main thrust of my talk will be to discuss how AI has to step in a big way and close the cost gap. Third, machine learning, as we have seen from the previous speakers, it all begins with big data. Fortunately, the semiconductor process equipment on the manufacturing floor is a very rich source of data. Fourth, at the chip and package level, away from the manufacturing floor, there are design breakthroughs. And they help implement AI, and they use AI to make the designs happen. But we see challenges in the cloud data centers. For those applications, there is an urgent need for effective AI for those application-specific semiconductors. Last, AI measures a major opportunity. But if we miss this window, then we may face an existential threat to future business growth. Okay, so as I said, Moore's law number 1, it describes continuous reduction in the feature size, critical feature size, which are nicknamed as nodes. For example, the Apple processor, M1 processor, is made at 5 nanometer node, and it packs 16 billion transistors in one chip. Brings multiple functions on the chip, like the CPU, the GPU, the DRAM, fabric switch, and so on. Then there are application-specific ASIC, system on chip, or system in package. A few days ago, Tesla announced the D1 chip with 50 billion transistors, and it's actually not one single chip, it's an ASIC SIP, system in package, that is designed to train AI networks in the data center and make, of course, automatic driving a reality. This is from TSMC. Their foundry is now the technology leader in semiconductor manufacturing. As you can guess, they are the people who made the Apple processor. Next year, in 2022, TSMC announced high volume manufacturing of 3 nanometer node ahead of everyone else. Sorry, having some trouble here. Okay, hold on. Too fast. Okay, below 3 nanometer, and for sure below 1 nanometer. The ITRS roadmap anticipates extensive use of AI modeling. And this is on top of new transistor concepts. So there's clearly many barriers ahead in continuing with the Moore's law beyond a couple of generations. Also, if you look at the red curve, you notice that the transistor scaling is now lagging behind scaling of the interconnects. Interconnects are shown in red. The interconnects also impact, and maybe more so, the semiconductor performance than the transistors themselves. And that's because of the RC time constant delay. Okay, back around 2013, in order to continue scaling, which is a linear scaling for the Moore's law, the transistors were becoming a problem. They could not turn out enough power, and then they were leaking. They went from being a switch to a dimmer. So the breakthrough happened, as it always does, so far thanks to the very smart people working on advancing semiconductors and keeping Moore's law alive. The breakthrough was 3D Finfet. The 3D structure greatly reduced short channel effects at 16 nanometer node back in 2013. We got major benefits of longer channel length, like higher drive current for speed and reduced leakage for lower power consumption. This slide came from Professor Jerry Gao's research. It shows how one can and one has applied machine learning to FinFETs. This way we achieve continuous improvement in all the transistor parameters. And that is indeed what's needed to continue with the Moore's law. But we anticipate in short time that the future FinFET structure has to be modified. And one idea being talked about is gate all-around design. There is a lot of history behind the slide here. Back in 80s, we had desktops and PCs. They were the industry driver. They used many single function chips, but on a big board. Then in 2000, came more capable chips like multi-core processors and 3D NAND flash. FinFET was introduced. And in 2020s, we have systems on chip and systems in package. And we see them all around us in the smartphones, in the servers, and soon in AI robots. So going to Moore's law number 2, which is the problem area. Let me just reiterate that for the first 50 years of Moore's law, there was a really virtuous cycle. Transistors were scaling down and cost was also going down. And this was true especially for DRAM memory chips. And they were the technology driver. But 10 years ago, this trend started to reverse, especially for advanced logic. A fully processed wafer with logic chips at 5 nanometer can now cost well over $15,000 each. This is 4 times more than the processed wafer cost for the 12 nanometer node 5 years ago. ML and AI, I think, and I know, can greatly help reverse the trend and get Moore's Law number 2 back on track. We'll try to discuss in the rest of the presentation how. So this is what I nicknamed the lost decade. There are many reasons why manufacturing costs recently started to go up so dramatically. Of course, they include the high cost of advanced lithography. There are many more process steps, now close to 1,000, and these are executed in batches of 25 wafers. But a more significant cost factor, in my opinion, is the silicon wafer size. It used to double, the area used to double every 3 or so technology nodes. And then the next wafer size will kick in. Equipment costs went up only about 10%. I know this because I was involved. And the fab output will double in the number of square centimeters or the number of chips, assuming the chip size did not go up too much. So basically, cost per chip went down for every wafer size transition by a factor of 2. And this continued until 300 nanometer node. This was back around 2001. And I was personally involved helping Applied make the transition. And we released 22 products in 1 year. Never done it before. But this happened and we dropped down in cost. But 10 years ago, we were due for the next size increase from 300 to 450 millimeter. And that did not happen for a variety of reasons. And so the cost in green, you notice, it keeps going up and up and up because of technology-driven cost. So this is the opportunity. ML and AI has to step in and get the cost back down and not wait for 450 millimeter wafer transition. Okay, one of the consequences of the last decade is a huge increase in the equipment capital cost. For state-of-the-art 5 nanometer factory, the capex is $5 billion. It is exactly double what it was for 7 nanometer node, which is the previous node. And that was the case a couple of years ago. This creates a huge barrier to entry for new manufacturers. Not healthy. It limits the market size and competition. So how does AI fit into this big picture? This is a simple schematic that at least clarifies in my mind how everything fits together. It all begins with big data, which we do collect, thankfully, in the production lines and off the production line. Next, the data needs to go through analytics, quite advanced analytics, and that requires algorithms for pattern recognition within each data stream, meaning there are many, many data bases, and this is a complexity. And then finally, we must implement ML and AI models for continuous cost reduction and performance improvement. So going to machine learning. This is a typical machine that is used to make semiconductors. This so-called Endura platform lived up to its name, and it has been very active, very successful for the last 30 years. Since 1990, it was doing only PVD film stacks, metal films. And then 10 years later, in 2000, it was able to do a combination of PVD and metal organic CVD films for integrated liner barrier. And then more recently, this year, Applied Materials announced a yet higher level of integrated processing for planarized copper interconnects. The schematic on the right side of the picture. To do this, the Endura has many single wafer reactors stuck all around it, and it can integrate not only PVD and MOCVD, but also ALD, atomic layer deposition, surface engineering, reflow, and even metrology. This high level of process integration sets the stage for advanced equipment that is needed now for 3 nanometer and below. Okay, the next picture is ASM lithography, ASML EUV system. ASML, as you know, is a Dutch company, but with operations around the world, including San Diego. It has been called the most complicated machine in the world. It costs $120 million each. But that's the price one has to pay to make features which are now going to go down to 3 nanometer, which is 30 angstrom. When you think about it, there's only 10 atoms wide. So this is simply amazing that one can do physical structures to the atomic scale. Even this machine, though, will require major new capability upgrade for 2 nanometer and beyond, according to ASML. So back to big data mining. As I mentioned earlier, it takes 1,000 steps to manufacture an advanced logic chip in a fab. These steps can be grouped by processes shown on the left of the slide. They concern deposition, lithography, and then etch. And the process sequence repeats itself many, many times. A variety of materials are involved. This is an enormous data mine within the factory. Begins with the test monitors to make sure that the machines are qualified for every shift. Then there's process wafers. And then post-process, there's metrology done on, again, samples or test wafers. So this is all the variety of sources we have for data mining, which then has to go through analytics, algorithms, and the algorithms do the pattern matching. And the last step in the process is to exercise feed forward and feedback loops that set up a new learning curve thanks to AI. So what are the benefits of going through this systematic and very powerful process. They're across the board in equipment productivity, yield, and the uptime productivity. They both can go up dramatically, even more so than today. A good example for equipment productivity is exercise predictive process control at lithography. And this is just beginning to happen now. So only by utilizing the full range of machine learning and AI, we can close the cost gap by at least 50%. One proof of this, a metric, will be to improve all equipment throughput to 60 wafers per hour, 1 minute per wafer. This is a slide from a McKinsey report, and the key message is worth taking home. It says, thanks to AI, we can move from experience-based decision-making to data analytical process. And so the decision-making is simply more reliable and more widespread. Shifting gears now, I'd like to go on to from semiconductor manufacturing to the end user world of systems. Now, before I go into case studies of those systems, let me emphasize that the entire value chain for the semiconductor industry, when you add AI modeling on top of it, is a major paradigm shift. It's going from semi-Gen 1 to semi-Gen 2. The AI will enable faster learning curve for continuous improvement across the board at every step in the value chain, going from bottom to the top. And it will set us on a faster learning curve, AI-driven, obviously, and maybe deserves to be called Moore's Law number 3. So as you see within the industry, we now have a new trend in semiconductor product design. It's going from function-based to a total solution-based chip, either system on chip or system in package. AI has found use in both approaches, SoC and SiP. You can see this example from AMD for Zen 3 architecture for their EPYC 3 server processors. This was announced earlier this year. The profitability of such a product depends upon packing more functions on a package. They have put in 40 billion transistors in one package, and also they met or exceeded performance benchmarks. They reduced the time to market. This way, they gain pricing power, market share, and profitability. Next. This is not a success story yet. The cloud infrastructure is a big, important segment of the electronics industry. And the industry, as you recall, used to be 3 C's: computers, consumers, and communications. To that, now we can add the 4th C, which is cloud. Also add healthcare. Also add self-navigating automobiles. So notice the scope of the electronics industry just doubled from 3 drivers to 6. And the cloud data center, which is very important in our day-to-day life and for security purposes, it faces a sustainability threat because of increasing carbon footprint. The semiconductors for this application need to be application specific to manage the high-speed networks and also manage the power. All of these applications, the new cloud, healthcare, and self-navigating automobiles, they are going to be utilizing AI in a bigger and bigger way. We notice the case of Tesla, but this is not a one-off. So, interim summary, we can clearly bring significant value by implementing AI and ML in the whole chain. And the chain can range from product design to manufacturing, including supply chain management, and including managing the carbon footprint for sustainability. Like every paradigm shift, MI and AL faces a critical window of opportunity. But in reality, behind the opportunity, there is also a threat. And the threat is simply, if we don't execute on AI, we impact individual company competitiveness and also slow down the end user market in a big way. Right now, there's a huge leverage. For a few $100 billion worth of semiconductors, one gets several trillions dollars worth of electronics. And we should always keep this in mind, that the semiconductor is a means to an end, and the end is electronics. Yeah, please bear with me. I have trouble with the last slide. See the conclusion. I apologize. Hold on one moment. Okay. You notice the frogs on the left. After the second frog, there's a barrier. And the barrier is labeled 450 millimeter. That was missed, but one can still leapfrog by cleverly applying the methodology of AI. It all begins with manufacturing, and that is the whole electronic industry's largest cost driver. There's a leverage. And electronics 4.0 will be only economically viable if we use AI in chip-based manufacturing. And then the payoff is faster piloting, real-time intervention in the process, and machine learning analytics to achieve 450 millimeter equivalent cost. So let me close at this point. Thank you very much again, and appreciate your time.
we have a question in the chat board. Sabahanka Dar asked the question to Mr. Sinha. Is Moore's law still valid today? That's the question.
The answer is maybe. Yes, part of the Moore's law, which is brute force scaling and putting more and more transistors, more functions on a chip, that is very much happening. And every time looks like Moore's law will come to an end. And there are so many smart people in the industry, it continues on. You know, even Gordon Moore said that it's really empirical. His law is not really a law. It's not based upon a basic physics theory of quantum mechanics. It's an observation. And it's an exponential observation. And Gordon Moore, in one of his famous sayings recently, said that no exponential is forever, but forever can be delayed. That's the mode we are in.
I have another question for Mr. Sinha. There is an acute shortage of chips today. How do you address that problem?
Yeah, that's very astute. You know, we hear in the news all the time that automobile deliveries have been pushed out. People can't go and buy a car and drive away because of shortage of chips. And it's not only the automobiles. So I think it's obviously a complex problem. The first thing people blame is the so-called supply chain. So the raw materials and so on, there's a disruption in commerce, there's a shipping problems, bottlenecks. So I think that's the easy answer. At a more fundamental level, it's a matter of not having enough supply, not supply chain, simply not having enough supply because the industry is becoming less competitive. The cost of the barrier to entry within the manufacturing industry is getting tougher and tougher. Not easy to raise billions of dollars just to build one factory. So I think the gist of my talk is by really focusing on cost reduction across the board, including cost of a new factory. I think that is the answer.
Maybe machine learning, AI can help with the supply chain management?
Big time.
Big time. Okay, thank you. Any other questions from the audience?
Yeah, Dr. Ashok, and I think this is a very exciting talk. You point to the new direction for future semiconductor and AI, right?
Yes.
So in your opinion, and for semiconductor people, what kind of message you should talk to them? So what kind of message you send to them?
Yeah, the message is it's a great opportunity, but with a threat just behind it. The time to act on it is already yesterday.
Good. How about for all these young computer scientists, those AI or data researchers? What kind of message you want to take to them?
I would suggest, obviously, these are very smart, capable people. Is just understand even at a superficial level the details of semiconductor manufacturing. It's not rocket science. And once you know it, you can begin to see the opportunities. If possible, if you can do some internship, try to get an internship in one of the semiconductor manufacturers. It's a different world from computer modeling, but I think it's a very exciting world.
Dr. Xing, you have been talking a lot about machine learning, but AI is more than just machine learning. For example, we have the symbolic reasoning, we have knowledge engineering, we have semantics, and multi-agent distributed AI, all these kind of things. In addition to machine learning, what's your view about other branches of AI might be useful for the silicon conductor industry?
Yeah, I'm not personally an expert in this area, but I would say you're absolutely right. AI is the superstructure and machine learning is part of it, but there's more to it. So AI as a whole is a bigger umbrella than machine learning itself. So with that caveat, I think interaction in forums like this is a great idea, and maybe this could continue not only in an annual forum, but in a more also workshop-like environment.
Thank you. Thank you. Very, very interesting answer to that. Yeah.
The question here.
Yes, please go ahead.
You mentioned system on a chip, but you also mentioned the scale of 3 nanometers, and you have AI apparently applying to the 5 nanometer and accelerating to the 3 nanometer. Does the AI also cover the yield for the system on the chip? And isn't that uniquely a different process?
Absolutely. It's a whole different application. And then the success parameters are different. And so system on a chip is a product, that goes to the end user. And for that, I think just getting the functionality of the chip without going through multiple iterations has a huge leverage. Just doing enough testing. A lot of the development cost is just the cost of testing so that no glitches and no bugs in the system. And I think automating that end of it is happening, and it has to continue in a bigger way.
The AI you're referring to will increase the yield on the wafer. I assume
Yes.
at 3 nanometers, this is
That's an imperative.
that most
Increase
extreme
yield on the
challenge.
wafer.
Yes. But what about that on the system on the chip as well? If you increase the yield on the wafer, is there a thought process on increasing the success? I would say the yield on the system on a chip as well.
Yes, that will follow. But I think system on a chip and system in package, require much more than just high yielding. Obviously, the chip won't go in unless it's a functional chip. But I think the problem is more complicated than just simply making a chip which is bad enough. But I think, in my opinion, system in a package, which is really what matters, because I think making chip bigger and bigger is not a good idea. All you do is lose the yield again. So it's making optimum size chip and packing them all very nicely in a 3-dimensional package, and getting that yield is clearly critical, and machine learning can help, because if you lose that kind of package, there's a lot of wealth by losing one particular unit out of 100.
I'd like to comment too on that, on the scale of the wafer going to 400 nanometers or 400 millimeters.
450.
I would have thought that the yield would have gone down because of the surface area and the probability of errors and mistakes that can happen in your yield. I was surprised that by increasing the wafer, you were getting cost effectiveness.
Yeah, I think this was a magic that I lived through a few generations myself, that the equipment is quite capable. And one basic parameter for all process equipment is uniformity from end of the wafer to the other end. And clearly defects have greater chance if the wafer is bigger, but the chip, mind you, is not getting bigger. It's just that you're packing more and more chips on the wafer.
The die size is staying the same size, you're saying?
It more or less stays the same, and it's limited by the field of, step and repeat cameras. They have only so much field of view.
Yeah, fringe effects.
And that defines the upper limit of the die size.
Yes. So the dies haven't changed. So
Not that much.
Okay, so the number of dies on, but the standard is 450 millimeters right now, and it's
No,
going to stay.
it's 300, unfortunately.
Oh, 300. It has not.
450 is the one that we missed.
Okay, we missed it, but you're saying AI would be the replacement for the 450
Exactly.
in terms of return,
Yes,
financial return.
yes.
Very well, very well. Thank you for your lecture. I have more questions, but I'll maybe another forum.
We can do offline. Thank you.
Thank you. I have a little bit of a background, but not
Actually,
deep.
we have time for a short question. If anybody else have a question to ask.
Ashok, this is Jane.
Yes, hi.
Very exciting talk. As an industry leader, we all know that you upgrade the whole industry from 200 millimeter to 300 millimeter, right? But now you're talking about the next leap to 450. How soon you think we can realize that leap with the help of AI and machine learning?
I think time will tell the critical path here. There's only one critical constraint, and that's ASML. If ASML can handle 450 millimeter wafer, then one can really push it through, depending on the number of customers that come together to guide the equipment people. But right now, there are not too many customers who can make chips. So it's a vicious cycle we are in. And in my opinion, we should not wait for 450, achieve the 450 benefits with AI at 300. And 450 will be a bonus.
Yes, we have been patiently waiting for more than 20 years for this leap, right? And the chips become more and more expensive. So in order for everybody to move forward in this trend, we definitely need to reduce the cost, and the 450 is the answer. So I think once you lead the industry to the next stage, and I think all the equipment company gonna follow.
Yes, that's the intent, that's the vision.
Yeah, just like you did for 300 millimeter.
Yeah, when that was hell, this is a bigger hell.